So researching rider behaviour. This was a bit of research we did. We got given 3 brand new motorbikes by Triumph. Here's a nice sprint here. On the second day of the research, it was a 5-day trip around the UK. We had people riding these bikes. The second day, somebody crashed their bike. I hasten to add that no motorcyclists were hurt in the making of this presentation or in the research. He did walk away. Potentially, though, he might not have done. It kind of underlines the dangers of trying to do research in the real world and some of the limitations that we have to face when we try and do research that applies to the real world. So, and that's another picture of the bike there. That's where it first ended up, and then we pulled it out by the side of the road for the picture you've just seen. The rider lost control on the bend. He said he hit a bit of gravel. It later turned out he was riding a bit fast with his friends, so peer pressure maybe played a point in this. So there are ways in which research can keep it real. We can go out into the real world and we can do real world research because that's the best place to do it. It's also probably one of the most dangerous places to do it. And so at Nottingham University, where I was stationed before, I've now recently moved to Coventry University, we actually developed a motorbike simulator to do some of the research in a controlled environment. And there's a whole host of issues there. I won't go through them all. I haven't got a lot of time. I've not timed my presentation, so I don't know how long I've got or how long I've been, but I'm sure you'll start waving if I go way over. But with a simulator, we can do lots of things which you can't do in the real world. We can give people identical scenarios. So if I ride differently and the gentleman over here rides differently, we know it's down to the rider, not the motorbike, not the environment. And that's something really powerful in terms of experimental control for research. So the simulator, there's a little picture of it in the corner there, is a full-size Triumph Daytona motorbike. We've got a big screen in front and we can design the environment to be whatever we want. And the rider uses the machine's controls to actually ride around the circuit, and we can monitor their behaviour. We can take many different types of measures of what the bike's doing. We can video the rider. And I was chatting to somebody again last night and saying it's amazing how many people jump on the motorbike. It's a full-size bike, so immediately they believe it's a real bike, and they start doing their shoulder checks as they go off. And there's nothing behind them in the room, it's just a black room. But they believe, there's a sense of immersion. Obviously there's a limitation to this. They're on a simulator, they know if they go 150 miles an hour around a corner and crash, they're not going to die. And that's one of the weaknesses of simulation. No, sorry, that sounded a bit wrong, didn't it? I'm not saying we should kill people, but you know what I mean. But we did a bit of research, and for the first time we were able to systematically test people's behaviour in different situations. And one of the things which we know about motorcycle accidents is that people tend to brake on bends. You get into trouble, you put the brakes on. And as soon as you put the brakes on, the bike sits up. And as soon as it sits up, it goes straight. And then you start to fall off the road and off your bike. But we also found that people swerved on straight roads. So they were more likely to change their position on a straight road before braking. But on a bend, they would brake before changing their position. And just knowing that simple sort of information was really powerful in understanding how accidents occur. And that happened across a range of different users. So just a quick example here of some of the research. We had a left-hand bend, people went around it a few times, and then later on in the scenario, they went around the bend and there was a car there by the side of the road, broken down, a clear obstruction. And we took lots of different measurements, but the key one we took was lateral position on the road here. And we had effectively 2 profiles. One is the advanced riders. So we had 3 different groups of riders. Advanced trained riders are the best in the UK. I'm saying that because I'm one. But they've had a higher level of training. They start off down at the bottom. They're going left around the bend there. And so they start off closer to the centre line to begin with. And they're not going into the bend as sharply to begin with as the other 2 groups. And so they see the hazard. They keep the observation line through the bend. They see the hazard earlier. They have to make less corrective sort of lateral movement on the road to swing out around the hazard. They're actually furthest away from the hazard where that green line and star is at the front of the obstacle. And you can obviously see where this is going to go with the next slide. The other 2 groups are virtually the same. The experienced and the novice riders, they come in a lot quicker into the bend. They go into the apex a lot sharper. So they compromise their view through the bend. They then have to compensate much more, and that takes them further round the obstacle, much closer to the centre line. Where they're past the obstacle, it's no longer a danger to them, and therefore potentially in the danger of oncoming traffic. So just by measuring these things in the simulator, it gives a very useful, very clear insight into the mechanisms or the way in which people negotiate these hazards, perhaps in the real world. So moving on to advanced systems and ITS, the picture on the right there is a ride that I did many years ago. I rode all the way around the UK and I tried to log it with a very simple GPS system. You'll see I got most of it, but not quite. I went through Wales and up the left-hand side of England and Scotland, and maybe my batteries ran out. I don't know, but or I forgot to turn it on. Such is the fallibility of technology and people. But some of the things which I was going through before the talk here, before I came here, and I was thinking of advanced systems. What can we get from what's out there in other areas of the world, other sectors? We've got things like 3D audio. We've got we can have microphones and speakers in the helmet that dictate where we look, because the sound will come from a position that will then alert us to something maybe on our left side or our right side or behind us or in front of us. I've done a lot of work in speech input, mainly for automotive applications, in-car entertainment and navigation systems. Trying to apply that knowledge to motorcycling would be quite useful if it helped free up some of the capabilities of the rider and not having to focus on maybe handheld and finger pressing when you're trying to hold on to your throttle and brakes and things. But it's a very hostile environment, a motorbike. Even if you try talking on a mobile phone, sort of hands-free sort of set or something, or even an intercom to a rider behind you, you know how difficult that can be. Other types of systems, I'll move on to move across these fairly quickly. Geospatial information for riders. So this idea of linking things together, as we've heard in a number of the presentations, providing just-in-time information. But it's a very short phrase, but it's very difficult to implement. What's just-in-time? What's just-in-time for me might be very different from what's just-in-time for somebody else. And we were talking about feed forward and feedback. Do we pre-warn people of something that's about to happen? And if so, how early do we warn them about it? What happens if there are a number of hazards and they start to overlap and the warnings start to get a bit complicated? Or do we tell people about something that happened? They've got through it okay, but can they learn from it and take that knowledge forward? We've talked about some of the eCall and Safe Rider type technologies that are out there to alert people when there's accidents occurred. I'm aware that time is moving on. And there's a whole host here of ITS solutions. I was actually amazed in the pack when I got it and saw that massive long list. I'm fairly new to ITS in terms of the technologies. I'm more about the sort of people and their requirements. And that's just a very short list, but the list in the pack is much more extensive. So how do we move this forward and think about sort of technologies? Well, there are things like helmet-mounted displays. We can learn from the military. They've got them for helicopter pilots and fighter pilots, so we can be sort of sexy and technology people too with these helmet-mounted displays. This is one that was designed for a motorcycle, clips onto the visor, tells you your speed, maybe the gear and such like that. It wasn't waterproof. It didn't market so well, for obvious reasons. Sat-nav for motorbikes, it's filtered down from the automotive industry, and I think we're in danger. I think we were chatting again over lunch and saying, well, the automotive industry is moving forward with ITS. Either we shout about what we need and want, or we just have to accept what comes through the automotive route and try and make it fit. One of the dangers here is that when sat-navs first came out for motorbikes, one of the big marketing things was you can use them with your gloves on and they're waterproof. Okay, well that's useful, but not totally useful for a motorcyclist, because often they didn't look at where they mounted, and people would actually have suction cups over their speedometer where they place the sat-nav holder. So this whole kind of juxtaposition of this sat-nav discounting the speedometer was quite a big conflict. And then we've got rear view helmets. I've actually got this one. I was going to bring it with me today, and I forgot to bring it on the train. But this is a helmet where you can actually see what's behind you, which is great in some respects, but not always. We've got a cyclist here. So unless they're the fastest cyclist in Brussels, once you've overtaken them, they're not really going to bother you again. It's ancient history. If you've got a passenger, I rode with my helmet on, and I had my brother on the motorbike because we did this big trip around the UK. So for 3,000 miles, I had him smiling at me all the time. Not the best view. Quite off-putting, really. And also at night time, if you're riding in the dark and you've got the brake lights of the cars above you that have passed you and the brake lights of the cars in front of you, there could be some sort of visual conflict there. How do we prime people to look at the right thing at the right time? And I think these are sort of generic issues which don't just refer to sort of rear-facing helmets, but also to ITS systems. So in terms of user requirements, and this is one of the areas that I work in human factors, it's trying to understand what people need and want. So again, we've heard about technologies that are out there, and the danger is it's a solution looking for a problem. We've all had accidents, we've all survived them. None of us are dead yet, are we? Don't think so? No? That's why presentations are really bad. So, in a way, what is the technology going to do for us? You know, I think very few of us actually anticipated that ITS would have helped us in any of the accidents we've had before. So what is it that we need and what is it that we want? So then, from that, what technology do we design to support those needs? So we can use formal methods within human factors. There are many different ways of going through these processes, but they often include these kind of iterations and participatory processes where we bring people in, we listen to them, we interpret what they say. Quite often we don't even know what we want. We're just told what the technology can do for us and we think that's what the solution should be. Let's try and look at what people want and need and try and interpret that into a solution which we can then build. Not very easy, bit of a challenge. And also this last one, I think, is managing expectations. We often think with speech input, when it first came out, we could talk to machines as easily as we could talk to people. We can't. We still can't. One of the things that my PhD thesis actually came to its conclusion was that speech input was actually another tool that we can use, but we need to be trained in how to use it. And I think from the ITS perspective, we've heard a lot of people saying that we need to be trained. We need to learn how to use these technologies and make them work for us in the best way, rather than just assume they're going to work infallibly. Because in Natasha's presentation, we know that an automated system, if it doesn't work, we then have to step in and recover. Okay, that's me finished. I'd just like to say a big thank you. There's my contact details, and I did leave out this morning some little handouts. There's 4 little articles that I put. I've got some spare copies if anybody wants them before the end of the day, or you can email me and I can send them through as PDFs. There's also a special issue of Applied Ergonomics which I'm editing later this year. So if there are any academics out there, and I think there's a few people put their hands up, and you're doing some interesting research and you want to publish it in a special issue that's focused on future transport, then grab my email and drop me a line and tell me what it's about, and I can pop you into the special issue. So thank you very much for your time.